algorithmic AI system creation. Now, I've been in this space now for about a year, and I've built many different types of systems for clients, for myself, for personal use. And I've been obsessed with this idea, especially because this technology is so new. I really want to push the adoption of AI forward. I think pretty soon there's going to be a lot of loss in faith of AI before it finally bounces back. And it's going to be up to people like me and potentially you watching this to pioneer solutions forward that are reliable, super helpful, and solve the entire problem of an industry or an avatar. This course is all about my experience in building solutions that stand the test of reality and solve problems all the way through, and not just for a YouTube demo. With all that being said, I've written some words, and we're gonna go through our script and we're gonna go to the video. So most people are building AI systems the wrong way. They focus too much on the model or the fancy agent that they created. They miss the main point. The AI isn't the product, this system is. A good system acts more like a game engine than a chatbot. Not in a video game way, but as a space for creativity and decision making. A game engine removes friction, making everything easier, and allows creativity to happen. The big idea is simple. The best software doesn't do the thinking for you. It gives you the controls. It helps you express your creativity without slowing you down. Think of tools like Minecraft, Photoshop, and Aidan. These tools don't hold your hand, they hand you the reins. You don't wait for the tool, it waits for you. And this is where AI shines, and I'm not seeing enough products yet that are being built like this. It takes the principle and enhances it. AI makes controls lighter and pushes the boring tasks into the background and allow you or professionals to focus on their craft. If you've played Minecraft at all, then you've probably played in creative mode. You know the feeling. Creative mode gives you every block, resource, whenever you want. You can fly, break blocks instantly without grinding for the materials. All friction disappears, and your imagination becomes the only limit. That's what creative mode means. No cost for thinking, exploring, or building. A great AI system should give that same feeling to a business. When you build AI with this mindset, your goal changes. It's not, I want AI to do the task. The real goal is, I want to remove the friction that stops people from thinking their best. And I really think that this is what's going to ease a lot of the fear and concerns and actually speed up the adoption of AI, because you don't want to push the humans out of the way. You want them to do what they do best, which is practicing their years of experience in making decisions and tackling problems. So the AI should assist in that, it should augment them. The real goal is to remove the friction that stops people from thinking their best. Create a space where they can run 10 scenarios in seconds, see consequences instantly, and create without hunting for data or digging through chaos. The idea is clear in construction. So where we work at Opulence is we're building this similar game engine, but for construction and contractors. So a contractor's engine is often a stack of Excel sheets, outdated Microsoft project files, and scribbled notes on their notepad and their brain. So it works, but it puts them in survival mode. Every decision takes effort. Every schedule change is manual. They have to dig for resources just to think clearly. They have to go figure out all their change orders, dig through emails, go through different client conversations. What we've been building at Opulence changes that. We provide contractors with their own creative mode, a voice-driven system that removes the grunt work around scheduling, planning, and scenario exploration. Instead of wrestling spreadsheets, they can explore freely through a dialogue interaction. Instead of hunting for information, they can just focus on judgment and pushing the project forward. Once you view AI systems as game engines, everything shifts. Your thinking changes. You stop asking what task can AI do and start asking, what's stopping this person from mastering their work? Where can I remove friction? When you design systems this way, users feel like the tool matches their thinking. Their creativity expands, their clarity increases, and the software becomes a support and an extension of themselves to become better at the skill. And that's where you want to be. You want to be ingrained in their workforce, in their workflow. So keep this core idea in mind. A great AI system acts like game engines. They give people creative mode. Once you grasp that, the next question is, what powers the actual engines? The answer isn't just AI systems, it's systems that run on algorithms, structured logic, equations, and predictable paths. The AI's job is to take messy human input and turn it into clean variables for the engine. The math, not the model, is the one that decides the decisions for the business. In the next module, we're going to break down what algorithmic AI is specifically and why it's the only way to create systems that actually solve the whole problem, and why I think it's the winning strategy going forward in the future. So algorithmic building means every single key decision in a business becomes an equation. Pricing, equation. Time estimates, equation. Risk, it can be calculated using an equation. So when you treat decisions like math, things become a lot clearer. You stop relying on AI to be smart or relying on its just underlying parameters, and you gain a lot more confidence in your system because you are the one who actually designed equations and algorithms from the ground up to represent the business that you're trying to solve problems for, and you can understand every single portion of that business. So rather than guessing, the LLM turns conversations between the user and itself into structured variables. Imagine someone saying, "It's a medium job, not too crazy, but not too quick either." The agent translates that into size equals 0.6, complexity is around 0.4, and then maybe a simple equation that doesn't make any sense is size times complexity equals 12 estimated hours. The AI extracts key data and converts it into variables for your equations to use. When you build systems this way, the output quality improves significantly. You eliminate hallucinations, inconsistency, and random answers. The LLM doesn't make the important decisions, it acts as the translator. Your equations make the decisions, and they behave consistently every single time. So to really nail this idea home, we're gonna go with a metaphor I created, and I call it the railroad example. To illustrate this, think of a railroad worker pulling a lever to decide which path a train should take. So you're the railroad worker in this scenario. You stand at a junction with a walkie-talkie listening for instructions. Based on what you hear, you choose the track. This is routing. Many early AI systems I built, and the still systems I built today, I use this type of architecture. An agent analyzes the input and decides which tool or function to execute. This is a great way to design systems. You're not trying to make one model do everything. You have one agent or a couple of agents making smart choices about which specialists should take the job. Should it go to the vision model, the code executor model, the API search model? The switchman's job is taking chaotic input and making routing decisions to route the train, which is the flow of data, or the query, to the best part of the system that is equipped to handle that. Now let's take this a step further to actually demonstrate what algorithmic AI is in systems design. So picture this. It's 1920 at a small railroad depot. You're a telegraph operator in a cramped office, lit only by a single light bulb. Outside, you hear a freight train approaching. Inside, the telegraph is chattering. Morse code from a dispatcher 50 miles away. Think of the dispatcher as an air traffic controller for trains. The message you're receiving is urgent, but it comes in as a stream of Morse code signals that only you can understand, or anybody that knows Morse code. So what's your role? You translate the Morse code into words and write them on a standardized slip of paper called a train order. These orders are rigid. Every variable has its exact place. Engine 10 meets engine 11 at Paris. Train 92 has the right of way. After you create the train order, you pass it to the crews, sometimes using a long pole so the train doesn't have to stop at all. I've been watching the Peaky Blinders, and they're in the middle of the Industrial Revolution, so I was kind of on that theme. Anyway, the crew reads that train slip and follows it exactly. That order supersedes any printed schedule, and it is the source of truth. So you're not making decisions or routing trains, you're doing what's called parameterizing. You convert signals, whether Morse code or messy input, into structured format that the system needs. You're the translator between human intent and machine execution. So let's actually go and map, in this example, what are all the components of the system, or the metaphor. So first, there's the dispatcher. This is your human user. They provide the original intent saying, find me something cheap, or move this freight train. But the request is like Morse code, unstructured user input, tokens. It's the raw prompt that a database or algorithm cannot directly understand, because it hasn't been built around it to understand, unless it's a large language model, and then it can understand it a bit. This is where the telegraph operator comes in. This is your large language model. Its job isn't to run the railroad, it's to be the core translator. It listens to the messy user input, parameterizes it, and it doesn't make the final decision. It turns that user's intent into a structured format. That format is the train order slip. That is the structured data, the JSON, the API call, the SQL query that the LLM outputs. It's the perfect formatted instruction set like sort price, price order ascending, signal variables, which we'll learn about in the next couple courses. Finally, that slip goes to the train crew. This is your deterministic code, your algorithm, your equation. This is the machine execution part. It receives the structured JSON and executes it perfectly each time. And that's what actually makes the decision, or that's what the end user or the business owner would look at and then make a decision based off of that information. Now we're going to take this even a step further. So imagine a vast railroad network. One dispatcher cannot inspect every track, bridge, and signal alone. So they rely on specialized crews, each acting as its own algorithmic cluster. One crew checks track alignment, another inspects switches, another monitors signal timing. The key point is that as we build a comprehensive system, which in this case would be a game engine, like we spoke about before, these crews don't just report straight back to the dispatcher. Their outputs become structured inputs for other crews. So the track crews report, track 17 is off by 3 millimeters, is a structured output. That same report becomes the input variable for the maintenance crew, which generates a work order. When the maintenance crew finishes, their output, track 17 repaired, that becomes the input for the signal crew's algorithm. And the signal crew's output becomes the input for the dispatcher's routing algorithm. This is your AI algorithmic powered system. You have many tiny railroad crews, small agents, running checks and passing clean structured signals to each other. The final report lands on the dispatcher's desks. They never see the raw chaos. They just get the necessary facts in order for them to make the decisions and make the calls. This approach works because it eliminates the two biggest problems in AI, randomness and inconsistency. If you let an LLM decide, it will give you slightly different answers each time. So if you just rely on an LLM looking at a business decision and you just prompt it really well, it's still, given the same exact inputs, will have a little bit of a different varied output each time. But if the LLM only extracts variables and the math decides everything, you achieve absolute consistency. You get the same variables in and the same answer out. So as you layer these small deterministic agents, you can handle massive workflows without losing control. The agents stay simple, the math is super solid and robust, and the entire system becomes easy to debug, scale, and trust. The hardest part is figuring out how it all works together. So you want to stop thinking about AI as this digital employee, and you want to start viewing it as a network of tiny tools passing around structured signals. So you're not building just one bot or one AI employee with a good prompt. You're creating an ecosystem where each piece has a specific role and is reliant on each other. Once this clicks for you, the next question arises. If the LLM is not the decision maker, how do you design the LLM to be a good interpreter of the input data? How do you build an agent that reliably turns human language into clean, structured variables that your equation can use? And we're gonna talk about that in the next one. When you hear AI system, it can sound huge and vague. So in this video, we're going to do the opposite. We are going to zoom all the way out on a business and break it down into simple buckets. More specifically, we're going to break down all of the processing and thinking powers that it takes to operationally run that business and put those into different buckets. And then we're going to zoom in on each one of those buckets and break them into very specific algorithms. This is the part where you actually just architect the game engine. We're not building any code yet or Aidan. We're really just having a conversation with ChatGPT to get our brain thinking. So the first thing you need to do is build your mind map. Under this video, I've put a prompt called Building the Algorithms, and that's linked in this module. So you're gonna go find the Building the Algorithms prompt. This is going to do a lot of the heavy lifting. So go grab it and paste it into ChatGPT and fill in the 3 blank values: your industry, your ideal customer, and the ideal result that your system helps them get or helps you get. So maybe it's residential construction, custom home builders, and win more profitable bids while hitting schedule. Or online fitness, and then the avatar is busy dads, and what they need to achieve is lose 20 pounds without counting calories. Whatever your world is, plug it in. What this prompt does is pretty straightforward. It tells the model, we're building a game engine. Reminds it of examples like the Minecraft and the Photoshop, and it reminds them that we're building an algorithmic system, not the random chatbots. And then it asks it to list all of the mental tasks it takes to run that business. It groups those tasks into buckets, and under each bucket, it proposes algorithms. The name, the purpose, and that's it. When you run it, you're going to get a long list, probably a lot more than you expect. That's good. It's just gonna vomit its ideas, and this is the raw material that you're then gonna filter down. So after you get this big list, your job is to whittle it down. You're going to go through every single algorithm it proposes and ask one simple question. How easy is it to get the input data for this? How easy is it for me to consistently get the data that it takes for this algorithm to actually execute? We're building solutions that make money and actually get used. So that means that they have to be valuable to the customer and realistic for you to feed in data. If an algorithm needs 10 different data points that nobody is tracking or the customers hate giving, that goes into the later pile. If another algorithm only needs a few things that naturally show up in conversation or are already in a form, that one moves up on the list. The ease of input will decide exactly what you build. So practically do this. Copy the algorithms into a Google Doc or a spreadsheet, and next to the algorithm, score it from 1 to 5 on input ease. 1 means this would be super painful to collect, and I would hate my life if I had to collect it every single time. And 5 means I could get this from a normal voice call or a simple form without anyone complaining. Go through the whole list fairly quickly and don't overthink it. You're just getting the feel for the system. So once you've done that pass, you'll start to see a pattern. Certain buckets will have a few algorithms that are both high value and easy to feed. Maybe it's scheduling, maybe it's lead qualification, and maybe it's pricing. Those are the best starting points. For the sake of this video, I'd tell the viewer to pick just 2 buckets that feel the most important for your customer and the most realistic for you to build. Inside each of those buckets, pick a couple of algorithms that scored high on the input ease. Those are going to be the tools in version 1 of your game engine. So once you've picked your 2 buckets and algorithms, we can start thinking about how this turns into an actual system. This is where the second prompt you wrote, the prompt for creating the game engine, comes in. So this is where you're going to go ahead and grab the second prompt, which is called the game engine prompt, and you're going to plug it in. So this prompt takes the algorithms you've chosen and asks, okay, what's the least number of workflows we can build in Aidan to make these tools work together? In other words, how do we wire this up so it feels like one cohesive engine instead of 10 random bots? You're going to paste in the algorithms you choose, and it will propose a set of workflows. This step is just really good to get you to actually start thinking about how this system is actually going to work. Because the reality of it is you actually might have one workflow that has 3 different algorithms within it. Not every single workflow needs to just have one algorithm per, it just depends on what problem you're solving. When you force yourself to list out every mental task in a business, you see where they waste time, where there could be some improvements, where they could make more money, and you see where a math-based answer would instantly make their day easier. Those patterns are the gold that you're trying to build in this game engine. So to recap, the homework from this one is grab that mind map prompt from the description, plug it into your industry, your ideal customer, and then the ideal result. Let it generate the algorithm list, then score each algorithm on one thing, how easy it is to get that data, that input data, and then pick 2 buckets and a couple of algorithms from each that score high. These are the tools we'll use going forward. So the next problem we have to figure out is how are we actually going to get data to come into our system? And that's when we're going to design a data capture inlet. And I'll see you in the next one. All right, so we understand game engines. We understand that decisions in a business can be represented by math as equations and algorithms. And now we even have started to get a better idea of what the very first version of our game engine is, and maybe a couple of algorithms that we're going to work on building. So now let's actually figure out how we're going to get that input data needed to make the workflow run into our system. So once you've mapped out your 2 buckets and you've picked your algorithms, you're going to build the next step, which is figuring out how this information gets in. I always start building any system with the exact same way, by getting crystal clear on the inputs of my system and then the outputs. This really demystifies everything else that happens in the middle of it and makes it so much easier to design. So your mind map gave you the outputs, now you need to design the inlets. The way you choose to interact with your system determines how the data flows. If you build a voice agent, you're designing one kind of inlet. If you build a static form, it's an entirely different type. Free text, journaling, Google Drive uploads, photo pipelines, maybe a combination of a couple. Each one shapes how clean or messy initial data is. So before you build anything, you need to ask yourself, which medium naturally fits how my user wants to communicate with the system? Are they most likely to talk, type, upload photos, check boxes? So voice agents are often the most natural way to collect data because people don't censor themselves when they talk. You get raw detail, nuance, and little signals that matter. But the downside is that voice gives you the messiest form of endpoint. Humans ramble, they backtrack, they change their mind. If you choose voice, you need a strong interpreter later in the pipeline to clean it up. Static forms, on the other hand, give you structured inputs right away. Drop-downs, sliders, multiple choices. They're clean, but they limit the way users can express themselves. They lose a lot of that nuance. Free text journaling sits somewhere in the middle. It's flexible, but still messy. Photo upload pipelines are powerful, but for anything visual, damage, site conditions, product quality, you have to build logic that can interpret what's inside of those photos. Every inlet has its own trade-off. So as the builder, you need to think in terms of data channels. A data channel is simply the path that information takes from the real world into your system. Voice is one channel, forms are another, photos are a third. Even pulling from an existing Google Sheet is a data channel. What matters is choosing channels that match the problem you're solving. If you're building an estimator and the algorithm requires a surface condition score, let's say it's an algorithm for a car detailing price estimator, we're going to need to know the amount of labor hours it's going to take, which means we're going to need to know the surface condition of that car. Is the paint chopped up is it super messy in the interior? You can't rely just on voice in that example. You might need photos too to interpret it. If the algorithm requires a bunch of structured numbers, a form might be better. If it requires story, context, voice, or journaling, that might make more sense. So here's a practical way to think about it. Take the algorithms you selected in the last module and write down the exact inputs each one needs. Literally list them. You want to ask yourself, what are all of the variables needed in order to make this decision? Because remember, algorithms are essentially decisions. So if you are making a decision on what electrical subcontractor you want to go work with, a one, two, or three, the variables that you need to know are how reliable are they, how experienced are they, and how much do they cost? So those are the three variables I need. And now I understand, okay, where could I go and get these different variables from the world in order to plug them into my system? And then ask yourself, what is the easiest way for my user to give me this information without getting annoyed? If a piece of data can be spoken, let them speak it. If it needs structure, give them a form. If it needs to be seen, ask for a photo. If it's something they're already tracking in Google Drive or Sheets, hook directly into that. Don't force your user into a channel that fights how they naturally operate. It's a really big turnoff, and that's a big reason why these types of software applications never get adopted, because there's too much friction in adoption. The job at this stage is to design the logic chain that moves you towards the final outcome that you want your system to produce. For example, if I'm building a detailing estimator, I know my final number depends on things like the interior condition, the exterior condition, the severity of the soil or the dirt, and the vehicle size. Each one of those comes from a different channel. Voice can give me descriptions, photos can give me visual truth, a form could give me simple yes/no questions or a quick rating. All of those inputs flow into my interpreter later, which turns them into variables for the algorithm. But it all starts here, designing the inlets correctly. So I want you to be thinking like an engineer instead of more of just a prompt guy. Engineers don't let random inputs flow into their system. They control it. They standardize it. They design channels that produce clean signals. And when you do that, everything downstream becomes predictable. So now that we have inlets flowing into the system, we actually need to, at this point, design the equation itself. And that's what we're going to do in the next one. All right, so once you know the problem that you're solving and how your data is getting into the system, the next step is to design the decision engine. Under the video, I've dropped a prompt called equation design prompt, and you're going to lean on that a lot because a conversation with AI is really going to help you model reality or what decision needs to be made into a mathematical equation. Because I don't know about you, but I didn't go to school for math. I simply just talk to the AI and it helps me. So you're gonna start by clearly describing the problem that you want to solve, such as, I want to score better lead quality, I want to estimate days for a remodel, I want to choose between 3 different subcontractors, I want to estimate the price of a detail. So the more concrete and detailed you are here, the better the equation is actually going to be. You really want to get pretty detailed in this step. So you're also going to want to identify all of those incoming variables that we designed and defined in the previous step. This is really going to help AI understand which variable is going to be a part of the equation to make the outcome. But then also taking that step further, you need to define how much each variable affects the outcome of the equation. And this is called weights. You describe how each variable should affect the outcome. This is where you slow down and talk to the model like a collaborator. So I was a car detailer before I started building software, and if I wanted to design a equation around a price estimator for detailing, I would probably say something like, in order to produce an estimate, I need to know the supply cost and the labor hours. So I would build an algorithm that would basically estimate the labor hours it would take to do a project. And then I would also probably create one that could estimate the supply drainage or how much supplies I would use. So essentially I would say, okay, everything that affects the labor hour of my equation would be the size of the car, the type of detailing package I'm doing. Am I doing exterior, interior? Am I polishing it? How dirty the interior or exterior of the car is, to what degree it is, whether it's raining or not, what's the weather like? That's a huge impact on the time it takes for me to detail. And then the location of the car. And the location means, do we have access to electrical and water? Now that I've kind of named all of these variables that affect the time it takes for me to clean a car, I now need to go and describe, okay, well, how much do those variables actually affect it? So I'd probably say something like, how dirty the exterior is usually does not have as much of an effect on the duration as much as the interior does. More simply put, if the interior is more dirtier than the outside, the car is going to take a lot longer to clean. I would then kind of brain dump and say, like, if I have to clean the seats, if they have significant soils or stains, if I have to vacuum dog hair, all of these things basically drive up the estimated duration that the detail should take. So you want to go and just brain dump everything you know about the problem you're solving, and then using that prompt template, AI is going to propose a weighted equation. And essentially what it's going to do is it's going to look at everything that you just said and it's going to say, okay, well, I understand that in this equation, if there is more interior dirtiness, there should be more time it takes. And that's all it is. So in my subcontractor example, I walked through a simple example where I had to choose between 3 different subcontractors, subcontractor A, B, and C. And I was basically grading them on 3 different variables. How much did they cost? How experienced were they? And how reliable are they? Did they show up to the job site on time? And I basically gave them a score from 1 to 10 on each category. But I knew as a user choosing these subcontractors, I really didn't care about price as much. I really cared about reliability and how experienced they are. So I would weigh them around a 0.08, and I would downweigh the price. I would make it feel like it doesn't matter as much. So then when you calculated the final output, it would take into account more the fact that I care about reliability and experience rather than price. This can be pretty simple or it can get pretty complex depending on what problem you're solving. So here's the thing. This is where you're going to lean hard on ChatGPT as your co-designer. You don't have to be the math genius. You just need to ask it 2 simple questions over and over again. How does the individual variable affect the output of the equation? And to what degree should this variable affect that output compared to the others? If you keep those 2 questions in front of you, the model can help you shape the formula. It will spit out equations with some extra fluff sometimes, weird exponent and random terms, and your job is to push back, and you need to question it. It's going to put back all of these exponents and stuff, and your job is to go and say, okay, why did you output this exponent here? Why did you put this here? How does that directly relate back to the outcome I'm trying to have? And you're going to force AI to explain itself, and you're going to say, okay, that makes sense. Or you're going to say, no, we don't need to take that into account. And you're kind of chiseling away and making this equation. So treat it like a conversation until the equation feels intuitive. You should be able to explain it to a normal person without their eyes glazing over. Okay, well, their eyes actually might glaze over. The last piece in this module that I'm going to talk about is what I call index tables. So once you've got your equation, you need to ask, what tables do I need so my parameterizer agent can feed this equation cleanly? That's why the prompt template has the recommended index tables. For each variable, you want to define the buckets, the normalized scores, and example values. So if one of your variables is kitchen finish level, you might create a complexity table that maps basic, standard, premium, ultra custom to 0.1, 0.3, 0.6, and 0.9. If the variable is lead intent, you might map phrases like just browsing versus ready to start this month into different scores. So essentially, these tables are resources that your parameterizer or interpreter agent is going to use in order to turn the actual incoming messy data into the variables that are going to plug into the equation that you just designed. So we're going to talk about this a lot more in this next module, which is actually building the interpreter agent. But just keep this in your head, where as we're building these equations, we want to also be thinking about what are the resources and tables that we need to build that are going to serve as a Rosetta Stone, or kind of a navigator, a compass, if you will, for the AI agents to interpret and turn the messy data into input variables. All right. We are now on to building the interpreter agent. So once you design the inlets for your system, you've decided if it's a voice agent, forms, photos, and you've designed your equation, the next piece is the interpreter, which is also called the parameterizer. You like my naming conventions? They make a lot of sense, right? This is the agent that sits right after the data capture and before the equations. Its entire job is to take messy human input and turn it into these clean variables before the equations, so that the math, your equation, can actually run. This is one of the most important parts of the system, and it's the one that you're going to be tuning. When I was first building this and I kind of just discovered this strategy for building AI systems, I was trying to build my master schedule builder for residential contractors. And the job was, through speaking to a voice agent, I needed the system to turn it into a fully fledged 180 task schedule so they could run their project on. And my first couple ideas for it was, okay, I'll just have the LLM, do a sentiment analysis, like understand the different questions that were asked in the contractor's answers, and then output and generate each one of those tasks itself. So the reality of this approach just blew. This was like 150 plus LLM calls, each taking a couple seconds, and worse than that, it was super inconsistent. Even with good prompting and good and bad examples that I gave it, the model would give slight different durations every single run. It would give slightly different durations for tasks, how long a task should take, every single run, even if it was the same exact inputs. Because that's how the models are built. They're probabilistic. And that's when the breakthrough happened. I was like, how can I whip a probabilistic model into fit perfectly into a deterministic system? Like, what the fundamental unlock for LLMs when it comes to system design is the fact that we can essentially now we can standardize a bunch of messy input data and just really easily reformat it into deterministic workflows. And the way software and systems are built is they need to be deterministic. They need to be predictable. So this was my way of doing it. I was like combining the probabilistic and the cool wide understanding that and the meaning making that LLMs have, and putting that into these deterministic systems. The mental shift is the interpreter doesn't make the decision. It prepares the inputs for the decision to be made. It listens to what the human says, reads what they type, looks at the context, could be a photo, and it outputs a small set of numbers or labels. In my schedule system, that's where the signals came in. I had a complexity signal, a crew signal, an access signal, and a size signal. Each of those was just a number between 0 and 1. The LLM's job is to say, given what the contractor said, the complexity here feels like a 0.62. The crew factor is a 0.1. The access factor is a 0.3, and so on. Then those numbers go into the equation and they auto-calculate for every single line item task. And that's what was able to actually accurately output the duration. So to make the interpreter consistent, you can't just tell it, think about complexity and hope it figures out. You need the index tables. So basically it's lookup tables that describe how words and situations map to variables. In the complexity signal, for example, I built a complexity index table. The table has rows for things like poor soil, tight access, custom steel framing, winter conditions, and so on. Each factor has a base weight that reflects how much it typically affects schedule duration. When the contractor talks, the agent scans for those phrases and multiplies three things together: the base weight, that reflects how much it typically affects the schedule duration; the severity, or how strongly they described it; and the confidence, how sure the model is that it understood it correctly. It sums those up and then runs them through a saturation curve so the signal doesn't blow up. A saturation curve is basically a brake pedal for your equation. It stops variables from going out of control when a bunch of factors stack up. So imagine complexity is made of 10 little things: soil issues, tight access, custom framing, winter, weather, all of it. If you just added them all together, the number would explode. The schedule would make everything take 10 times longer because it would be, oh, it's super complex, which obviously isn't true. So the saturation curve keeps that from happening. And AI, when you're actually designing your equation, is going to propose different types of exponential decay and exponential, these saturation curves. And your job is to say, what does that mean? And why did you do that? And it's going to explain why it did that. And you'll be like, okay, I think I understand that. So the end result is a single complexity number between 0 and 1 that actually reflects reality. The same pattern repeats itself for other signals. The crew signal compares the contractor's actual crew size to the baseline crew size that the original schedule was created for. If the schedule assumes 8 people on site and the contractor says, I've got 10 guys, the interpreter calculates a crew delta, or the difference between numbers. So in this case, it would be two extra guys, and then it clamps it so it can't explode past a reasonable range. A clamp is very similar to that brake pedal or saturation curve we were talking about. More crew speeds things up a bit, fewer crew slows it down a bit, but it never goes insane. The access signal uses an access index table, which takes phrases like, if they mention them on the conversation, a cul-de-sac, lane closure, boom truck, narrow driveway, all of those map to weights that I created between 0 and 1. So the size signal compares the actual square footage to the baseline square footage, again clamped so that huge projects don't send the math into outer space. 4 different agents, each outputting one number, and that's the interpreter layer in practice. If it still feels abstract, let's zoom out and go to a simple subcontractor example. So we're gonna go back to the algorithm that's just supposed to decide what the best subcontractor is to choose for a job. So you have 3 electricians to choose from, A, B, and C. You scored them each on reliability, skill, and price. Then you assign weights to those variables. Reliability matters more than price, for example. And then you use an equation to calculate a final score for each subcontractor. So from an implementation standpoint, you literally bake these index tables and rules into interpreter's prompt or attach them as tools. So you can create the index table in the prompt. You just kind of make it as a CSV format, and you say, refer to this index table for when you output your number or your variable. Or you actually give it, like I used Aidan's data tables, and I use that as the index tables. So you spell out in plain language and in tables how to map words or incoming data to variables. If the user mentions X, bump complexity by this much. If crew size is bigger than baseline, calculate this delta and clamp it here. If square footage is between these values, set size to that range. The model isn't being smart, it's just following your rules. And it then grabs JSON from the interpreter, passes it into the code node. The node runs whatever equation you designed. Maybe it's a weighted duration formula, maybe it's a lead quality score, maybe it's a bid recommendation. The point is the equation is now running accurately, and the variables that are coming into it actually reflect reality of what was described in the incoming data, because your interpreter agents or parameterizer agents have their index tables, and they have a good prompt that basically says, when I see incoming variable thing, I should go map it to this value in my index table, which means I should output this number, which is the final variable to be plugged in. So when we boil this module down, the interpreter is the layer that turns unstructured input into structured signals using index tables and clear rules. Doesn't make the final decision again, it just computes the variables. The equation, the math, is where the decisions live. So at this point, you're really ready to plug all of your variables into your equation. So your equation is going to be outputting things, but the next step is how do we actually run evaluations and tune the system over time? Because I can bet you the outputs of your equation in the beginning are not going to be accurate and reflect reality. So we have to tune them. And that's what we're going to talk about in the next one. So once your equation is built and your interpreter is feeding in clean variables, the next step is to make sure your system actually behaves well in the real world. Because no matter how well you design your first iteration of the system, it's most likely going to not behave up to reality standards. And this is the one thing that a lot of people don't actually acknowledge when building AI systems is most of them take a tuning period where you actually need to tune the different knobs and make sure that the outputs of the equation or the system are reflecting reality. Your equation might overreact to one variable and underreact to another. None of that means your system is bad, it just means it hasn't been tuned yet. So the way you tune these equations comes down to two levers: your index tables and the weights in your equation themselves. That's it. Those are your knobs. When the system is too aggressive in one direction, it's because the index table is giving too high of a base weight or too high of a severity multiplier. When the system isn't moving enough, it's because a variable's weight is too small or the table ranges are too conservative. Everything comes back down to those two components. And the beautiful part is, once the interpreter and the equation are separated, tuning becomes simple. You never have to mess with the prompts again. You don't have to pray the model behaves, you just adjust the math in the tables themselves. The real skill here is building a feedback loop that makes reality really easy to capture. If a contractor says this task normally takes 3 days, but the system gave me 5, you shouldn't treat that as random feedback, you should treat it as data. What variable did the interpreter output? What weight did the equation apply, and which table contributed to it? Which knob needs adjusting? Every piece of unexpected output should point directly to a place in your logic that needs to be tuned. When you're architecting the system well, the whole thing becomes super debuggable. Here's kind of the tuning cycle. So first take real-world examples where the system produced close but not perfect. Look at the variables that the interpreter produced. Were they too high, too low, too sensitive to certain keywords? If so, you need to adjust the index table. Maybe that specific phrase shouldn't map to a 0.7 severity. Maybe it belongs to 0.4. Then you look at the equation weights. Did one variable overpower something else? Did complexity dominate what it shouldn't have? If so, you either push that weight up or pull it back. Then run the example back through the equation and see how the output changes. So now if that matches reality, that's great. Now you just keep iterating from there. This is what AI models do under the hood, just millions of times a second. The more examples you run, the cleaner the system gets. After 20 or 30 real-world samples, the system will feel shockingly accurate. Not because the AI magically improved, but because you tune the math to behave exactly how a real expert behaves. And that's the essence of the algorithmic AI. And I'll let you in on a little secret. This sounds like a lot of work and really annoying and really anal, but guess what? This is how you make a shit ton of money, because you're basically developing proprietary data where you can take and say, hey, I just built over 3 months a system, a math-based estimation system, and I created and captured proprietary data for the West Coast for car detailing. And I can tell you that my equation, if you plug in your rates, will give you a estimate in 10 seconds that is 95% accurate. And that data becomes so valuable. And that's like the heart of why data, good data, is so valuable. It's because the data that you capture and feed intelligently into your systems is the gold that basically predicts reality and makes everything more efficient. So here are some examples that I kind of just jotted down. So if the complexity table is too sensitive, so you might run into something like a contractor tells a voice agent, yeah, the soil's great, but it's not workable. The interpreter maps not great to a complexity severity that's way too high, maybe a 0.8. And suddenly, every excavation task balloons in duration. The contractor sees the output and says, dude, this should only add maybe 1 day, but not 3. That's when you open the complexity index table and realize you made the phrase like not great or kind of rough too heavy, so you tune it. Drop these base weights, tighten up the severity range, and rerun that same example because you capture that input data. And then you know, like you just said, it should have taken 1 day. So you're gonna tune it until that output of the system is 1 day. And then you're gonna keep those weights. So example 2 are the weights are wrong. So if you're tuning a pricing formula for detailing, let's say your variables are vehicle size, interior severity, and exterior severity, and pet hair. You get a case where the customer says the car's big, but honestly the inside is pretty clean. the system spits out a price that's way too high. Why? Because in your equation, the size weight is like a 0.9, and the condition weights are tiny. Size is dominating the entire formula when, remember, previously we said it's actually the severity of the dirt or the grime inside that really jacks up the time and the price of a car. So in that case, you'd pull the size down, you'd bring the condition weights up, and you'd rerun the scenario. So in these examples, what's really important is you need to have an expert. You need to have somebody that can look at the system and say, this is either good or bad, and by how much. And it's monotonous and it's tiring, but guess what? That's what it takes to build systems that are really accurate and valuable, and will make you a shit ton of money. It's work. Who would have thought? So that's everything I got for the system tuning. The next step is I'm actually going to walk through and utilize all of this framework I proposed and build an algorithmic game engine, but for detailing, because I love car detailing and I haven't done it in a while. So I'm not exactly sure what I'm going to build yet, but you'll see what I build in the next one.